All right, calculus. We're going to be doing problems 6 and 7 from lesson 2 in the summer work. So as we go through this, just try and keep up as best you can. Remember, you can pause, rewind, go at your own pace later. But we're going to keep on moving here. All right, so we're driving on the highway. And right here we got a velocity function. It says v of t, meaning velocity, or that's kind of like speed. Even though there's a difference between them, that's kind of what we're talking about. So we got this velocity thing. And it says we're traveling right here at 100 feet per second. Then all of a sudden, we see a policeman. Pardon me. And then the policeman kind of encourages us, I guess, to drive a little bit slower. So then we drop down to 60 miles an hour, it looks like right here. So what does the velocity seem to be between t equals 20 and t equals 30 seconds? Well, here's 20, here's 30. So what's this velocity? It looks like it's right at 60. So I guess it only took us about 20 seconds to slow down. So it looks like it's 60. Now we got to use units. Well, this side is feet per second here. So that's actually what our value is, 60 feet per second. But how far did we travel? Well, there's an old function, or not an old function, an old relationship. Talks about distance. Sorry about that. A little interruption. Anyways, we're talking about this distance relationship, and the distance equals rate times time. And when you're doing distance equals rate times time, all you got to do is know what your rate is, know what your time is, and then you can figure out distance traveled. Well, in this case, we're looking for distance, and we have a time interval. We're going from 20 to 30 seconds, so that's 10 seconds. And then we also have a rate. It's 60 feet per second. So if we did 60 feet per second times 10 seconds, well, our seconds are going to reduce, and we just go 600 feet. 60 times 10 is 600 feet. Now it's saying, explain why the answer above can be expressed as the area of a rectangular region on the graph. Okay, so look at this space that we're talking about. We got a top edge here at 60. That means that this side of the rectangle would be 60 feet per second. And here we got 10 seconds. So we have this rectangle that we could shade in here. That means that the area of that rectangle represents the calculation that we just did. So why does it work that way? Because D equals RT, and R and T are the sides, are the dimensions, I guess, are the base, and height of the rectangle. Rectangle. There we go. Let's take a look at this next one. Distance you travel between 0 and 30 can be represented as the area of a region bounded by the graph. Okay, so we're talking about this area underneath the blue line, all of it. Estimate the area of parts of the rectangles to the nearest. Oh, wait, what's it saying here? Count the number of rectangles. So each of these boxes counts as a little rectangle, I guess you could say. So how many do we have in this one? 1, 2, 3, 4, 5, 6. So we got 12 in that box there. And this is 1, 2, 3, 4, 5, 6 times 4. So then this box here, the rest of it to the beginning, if we kept that 60 feet per second height right there, is going to be 6 by 4. So that's 24. And this was 12. Together that's 36. Is that correct? 1, 2, 3, 4, 5, 6. And by 2. And then by 4. So that's 36. And then we got another one here. So that's 37, 38, 39. I'm just going to say it's about 39. So I'm going to say it's about 39 rectangles, give or take. I mean, it says to estimate it to 0.1. I think 39 rectangles is a pretty good estimate. How many feet does each small rectangle on the graph represent? Okay, so looking at this, each rectangle is 5 seconds times 10 feet per second. So each of those is going to be 50. So each one is 50. There's about 39 of them. So how much is that going to be? That's going to be, what, 3950? No, less than that. About 1950. Let's actually calculate it here. 39 times 50. 39 times 50. And we get 1950. 1950 is that total area. Of all those rectangles added up, it's about 1950 feet. So now we're talking about this problem. It's the area under a curve. That's the key thing that was mentioned here. It's calculated by estimating a product of t and y value. That just means your horizontal and your vertical, your input and your outputs. It's called the definite integral. That's a key word that we're going to come back to a lot this year. But definite just means defined, and integral just has to do with the process of finding area under a curve. Since t is measured in seconds and y is measured in feet per second, so we're going to have this product of feet per second times seconds, and that second's always going to cancel out. So it's always going to be measured in feet. All right, so that's number 6. Let's take a look at number 7. This one's very similar. It's saying people line up at a concert to purchase tickets. Okay, so they're lining up, and the rate at which they line up is this graph here. It's a rate for the people that join the line. So if we have the accumulated rate is going to equal a total, and that's kind of where we're going with this one. So this time the definite integral, otherwise known as the area under the curve that we've been looking at, from 0 to 20 would be this box here. Now keep in mind this is 5, 10, 15, 20, so it's 20 on this side and 10 right here. So that's going to be 200 people. The next one is from 20 to 30. So that's from here to here. Now I'm going to cheat a little bit. This is a trapezoid, but I'm just going to do it as a triangle and a rectangle. So if you look at this, it actually looks like a triangle and a rectangle split in half. So this rectangle is 10 by 10. It's actually a square, I guess you could say, even though it looks more rectangular shape than these units. So that's going to be 100 there. This was 200, by the way. And then on top, we got this triangle. It's 10 wide by 10, 20, 30, 40, 50 high. So a triangle is half of a rectangle, so it's going to be 10 times 50 divided by 2, or 250. So 250 and 100, that total area is going to be 350. So that's 350 people. Now from 30 to 35, now we have a base of 5 and a height of 60. So this one's going to be 60 times 5, but it's a triangle, so we got to multiply that by a half. So we wind up getting 350. Again, is that right? No, that can't be right. Let's double check that. 60 times 5 is going to be 30. That's going to be 150. There we go. 150. The definite integral from 35 to 55. Okay, now this is where it gets a little weird, because you look at this and you're like, okay, that is an oval. I don't really know how to find the area of an oval. Well, let's look at this so-called oval. The vertical radius here is 10. The horizontal radius here is also 10. So that's not an oval. It's actually more of a semicircle that we're looking at. So it's half of a circle. That means we're going to do half pi r squared, because pi r squared is the area of a circle. And our radius in this case is 10, so it's going to be half of pi times 10 squared. And 10 squared is 100, half of that is 50, so this area is 50 pi. 50 pi. What's the definite integral from 0 to 55? Well, if you got a whole bunch of areas, and all together they add up to the total area, it's just the total from A through D. Now I'm not going to work that out because you guys can add numbers, but that's what you should do, is add those numbers up. All right, we're going to take a quick break. See you in a minute.